Welcome everyone to today's live stream. Some more in-depth computer science stuff here. Because obviously we prepare for the future. Certainly RISC-V is coming. Many people already talk about this. RISC-V, of course, a new open source and free instruction set architecture that has already the first silicon implemented, not only some years ago for scientific proof of concept, but also in latest times with new startups, High5 or Sci-Hive or I don't even, whatever. Anyway, and so there was also RISC-V Unleashed and something. The reason I don't have this hardware silicon here is that we are here open source developer and stuff, so I can't afford to buy each and every latest and greatest new research silicon, otherwise I would not have any savings left. So we prepare here, of course, the stuff is already running. So here I have T2 cross-compiled on the data center, and also probably could have, did I move it? Anyway, tested this here. So it's also, so this is in T2. You can build this today. You see this is here cross-compile RISC-V, and here's a disassembly. And I wanted to discuss quite some details of RISC-V already to give you here some better understanding. Also, for those who have never seen this will also be a relatively quick guide here through how CPUs actually work at all, on a very rough high level. So I probably will make in maybe 6 or 12 months or something a more detailed video about how CPUs actually work internally. Also, we probably most likely have FPGA work coming, because you can have a RISC-V implementation certainly on a FPGA if you have a tiny enough RISC-V implementation and large enough FPGA. So anyway, so let's get started here. So RISC-V, this is the official, you see here RISC-V org user level instruction set architecture version 2.2. So instruction set architecture, what does it mean? That means instruction set architecture, this kind of documents define the specification, the interface to the CPU, how the CPU, like the language of the CPU, what you feed the CPU in terms of like numbers of machine code to actually work. And that is the biggest and only sort of kind of difference between like x86, PowerPC, ARM, MIPS, all the different instruction set architectures, because certainly they are all entirely incompatible. So this is why you just can't run MIPS on ARM and x86 on PowerPC and stuff, because certainly all these numbers don't add up. And with this RISC-V coming, I thought it's a good time to take a closer look here. What is interesting in RISC-V? So RISC-V is also a relatively modern instruction set architecture, because all the other ones, not only x86, which by the way is complex instruction set architecture, and I will show you briefly what that means. Of course, RISC-V has already reduced instruction set architecture in the name. So this is reduced instruction set architecture, which I personally favor quite a lot for keeping it small and beautiful and simple to implement, power efficient and so on. And what is interesting with RISC-V is that you have here different kind of sets. This is RISC-V 32I for integer, I think. E was it embedded? Anyway, we will see this in a second. And also extensions. So by the way, it's not fully frozen. So for example, here frozen, you see here some are not yet frozen. For example, F is floating point, 32-bit floating point. Then we had, was it D? Maybe D was double precision floating point. Q is quad, like 128-bit floating point. And also there is compress, so that should be probably here. C is compressed instruction. Extension for more compressed instructions. I will show you in a couple of minutes what exactly that means. So what does it mean? That means there is not one RISC-V implementation, but there are many. So if you choose to implement a processor either in an FPGA, field programmable gate array, or actual application specific integrated circuit, like a real baked dedicated designed logic gate set that you defined and layouted and stuff, because FPGAs are flexible, you can just program. That is the difference between those expensive programmable and custom ASICs that are specifically tailored to your like an Intel Pentium that Intel designs. Quick shout out to the audience. Welcome everyone. Nice to see you here. Recurring fans and stuff. Danny, Christian. There is a lot of progress in T2 that is thing for another video. Also, I updated this RISC-V stuff here. So this is here compiled on cross-compiled on T2 because I'm waiting for getting silicon into my hands. And Christian, RISC and CISC have gotten really blurry these days. Most RISC processors have more instructions than 68,000 and one considered CISC. Yes, and I will show you in a second. Also, by the way, fun fact, RISC-V is predominantly big endian, little endian, sorry, which I'm not the greatest fan of. However, you will see in this document that the RISC-V inventors leaves us open, so theoretically it is possible to create a big endian RISC-V processor. However, I will show you one point where I understand that having this little endian makes one thing easier and more efficient. So let's take a closer look here. What this means is that you can, if you want to build a processor, you can define you want it 32-bit, 64-bit, or even 128-bit, and what kind of extensions like floating point, double, quad, compressed, and so on, what you want to support. And that means you can have a processor tailored for very low-level embedded implementation, like a hard disk controller. I think like Western Digital or Seagate or some companies wanted to use or joined the RISC-V Foundation for exactly this very low-level embedded processor controllers, and even like maybe NVIDIA is using this or wants to use this for future NVIDIA power management on their graphic cards. So on future NVIDIA, not that we support this here, totally not a fan of NVIDIA, but I think they announced somewhere that NVIDIA is adopting RISC-V for at least the power management control, which is of course a very, very tiny part of a GeForce graphic card. So yeah, and yes, Christian, in theory I'm a big endian fan. Maybe we talk about this. So I try to keep this video a little bit brief. Maybe we can try to go through this in 45 minutes or something. And so you see here quite some revisions. Obviously this RISC-V was not invented yesterday, so this is like a 10 or 15 year development. It comes from universities there, Berkeley or wherever that was, something like that. So it's researched for a decade or longer stuff. And I only wanted to show you, so you see all these extensions, non-standard user. Here you see, by the way, the extension. So as I said, single precision, F is standard, A was for atomic instructions, of course, how could I? And also, yeah, M for integer, multiply and divide, and double precision, quad precision, and decimal floating point. And you see some of those are not final version 0.0, and also, yeah, compressed. What I find really interesting is compressed extension for compressed instructions. That is pretty interesting. And I will not go through all of them. I only wanted to show you how this looks internally and how processors work. Of course, you can take this for your holiday. It's a nice read on the beach, together with a Muller report or something, allegedly, I heard. Anyway, so what is different in RISC-V to many other instruction set architectures is that because it is so modern, they could already work in some things, for example, for these extensions, and that makes, in my opinion, RISC-V rather interesting. Not only that you can build a processor without all those kind of extensions, a very small, like you could call it Pico RISC-V, which apparently Clifford Wolf here of Rock Linux creation fame did. So if you're looking into FPGA Pico RISC-V, it's there from Clifford Wolf. You can go to GitHub and use that. And what makes this very interesting is that it has built-in support for this compression extension, because when you compare this to other architectures, let's take a look on the base instruction set. So of course it has really many registers, like 32. The size of these instructions of these registers is X-lang. X-lang is either 32 or 64-bit. This is also what you would define in GCC, glibc, and T2, of course. If you compile for RISC-V, you need to configure you want to compile it for 32, 64, 128-bit, and then all your registers, all your 32 registers are of this size. And yeah, 32 general purpose registers and current executable instruction counter. And so here we come to the actual core of the specification, which is a base instruction format. And you see here these instructions, you have here R, I, S, and U type. And what this means is that certain different instructions like move, and this is how CPUs work internally. You have instructions like move, multiply, move of course moves a value around, or load and store, load a value from memory, store a value from memory. And this is a huge difference between RISC, reduced instruction set, and complex instruction set architectures, because on x86 you have instructions that are not so clearly divided. On x86 a lot of instructions can actually load and store values from memory in one instruction, and on RISC you usually have load, store, and arithmetic instructions like shift, divide, and so on, and or, and all this kind of logical stuff. This will be a rough summary. Maybe if this kind of video content is successful, maybe I make a dedicated video explaining all this kind of stuff. I guess many people in the audience know already how logic works, binary logic, like ORing stuff, ending stuff. But if you don't know, leave a comment below. Maybe we make a dedicated video. So what this means is that certain kind of instructions are encoded differently. For example, so here this is certainly an immediate load instruction. Immediate means here's a constant value, like you need a special value. Say you program a voodoo card as 3DFX voodoo card, and you need to write a specific value, magic value, like texture, a 3D triangle. You might have there a very specific value, a bit field like 2100 something, and this kind of values could be encoded here directly immediate, for example. And this is why this base instruction formats have different formats, because you cannot just press all of those different instructions in one type. This is why we have different ones for immediate values. You see here the immediate values can only be smaller, and then you have different functions. So the opcode is here formed of the base opcode stuff plus usual this function, which usually defines more bits for this kind of opcode. So if this is like arithmetic stuff, then this function 3, for example, might further clarify this is an AND, an OR, and so on. And this is basically how all the CPUs work. If you ever wondered how your program works internally, this is how it does. It loads a value and then decodes this, decoding meaning the logic in the processor takes these bits apart, and then from the opcode, the opcode here might be like 6 or something. We take a look in a second how these opcodes really look like in practice. But let's say this is the opcode is a 6. 6 might mean logical shift or something. You know, we had some frame drops. And then the processor is performing this specific function and then continue at the next address. That, as you see, these are always 32 bits. So then it's continuing at the next 32 bits, which are 4 bytes. So it's advancing the internal counter, program counter, or whatever you want to call it, to the next instruction, and starts all over again, decoding this opcode here and so on. And what I find particularly interesting here when we take a look, this is, by the way, exactly what you see here. I think RISC-V, is it even maybe not fully on? So as you see here, run here some disassembly. By the way, we have some frame. No, we have quite. Why do we have such a high frame drop now? Do we not have a? Don't tell me our. But now the frame drop is more stable again. So it's not TG3 then. Anyway, I hope we resynchronized here with the internet. Really need to watch this frame drop. And so yeah, so here's some object. Oh, by the way, I could test if our data center still works. Then TG3 works, can't really mix this up. So this is how you do a disassembly here on Unix systems with a GCC, with a GNU toolchain, RISC-V 64. So this is a real binary built last night or yesterday. Dash capital D for disassembly. This, by the way, is a hello world. I previously compiled here. How do you cross-compile? You just run RISC-V 64 T2 and so on GCC. Here's some hello world example, static size optimized stripped, and then you can disassemble it. What is, by the way, I wanted to point out that this is disgustingly huge. So this is glibc, hello world in today's binary blow, 293K for an hello world executable. Thank you for that glibc, just in case you wondered why we are migrating a little bit away from glibc and have diglibc support and uselibc and musl. Anyway, so disassembly, and this is how the instructions look like. 32-bit instruction here. Let's take maybe a look on a branch. This is certainly branch not equal here, I would say. And here you see the registers and some value. Maybe this is some immediate value here, I would guess. And this is the instruction. Now you might say, wait a second, did you not say a second ago that the instructions are always 32-bit? And what is this stuff here in between? And yeah, so this stuff in between here, the 16-bit instructions, are actually compressed instructions, and that is what I wanted to mostly point out. Welcome in the audience anyway. So this is a big difference between most other RISC architectures, this compressed extension here, and this is pretty cool. And you see, we do not always say that everything is peak bugs here, something's also really cool. So how does this work? Let's scroll for this to the compressed instruction to take a closer look. And then I will show you how this differs to PowerPC and Spark. So you see, by the way, here you see all the load and store instructions. So you see here load, store with some offsets, base, width, and so on. And again, this is how instructions, how CPUs work. This RISC here is RISC-V, certainly a very nice read for your education, for playing along at home. And let's see, base, integer, instruction set. So I think this was E for embedded or something subset. E for integer computational stuff. Let's go to, maybe I should have M for standard. So like Spark, the original Spark processors also didn't have integer multiply and divide. Original Spark 32 from 1990 something, they only had some integer multiply steps, so you maybe had to run this for up to 32 rounds on the first Spark Silicon in 1990 for the first Spark Station 1 or whatever that was. And also here you see this is an optional extension, so for RISC-V, if you wanted a very small processor that is extremely tiny, like a PicoRISC or something from Clifford Wolf for your FPGA, or extremely tiny silicon, you could have a RISC-V processor without integer multiply and divide. And then if you need integer multiply and divide, you need to construct it with a software routine from other logical instructions and loops, like shifting and such, all the bits around until you have all the rounds of an integer divide and multiply. So compressed extension, yeah, atomic instructions. And then we finally reach, of course not, let's finally, should have searched the CSC for compressed. And what this is doing, and this is a huge difference to other instructions, because when you take a look, PowerPC either, you see this is similar here with PowerPC. This is here the official PowerEiser version 2.07 public. And you see here the concept is entirely the same. They have a different instruction formats, 32-bit, and different forms, I form, B form, and so on for different kind of opcodes. And then the big difference is, so this looks relatively similar, although actually quite some exceptions. I personally find this a little bit disturbing how many different forms this PowerPC has, so much to keeping it reduced and simple. But the huge difference is on PowerPC, as far as I remember, all these instructions are always 32-bit. So this is a huge difference. What I also called out, I made once this huge benchmark of all the vintage systems from SGI Octane to SparkStation and such. If you're interested in this, you can watch this previous video. But this is why x86 has one of these advantages, is that the x86, the complex, very, very complicated instruction set is variable length. So you have some instructions on x86 that are only 1 byte long. For example, maybe increment or stuff like this, or some move, maybe move one very special, move something to something, or maybe even interrupt, software interrupt. 3 trigger might be like 1 byte maybe. And then you have additionally to this variable length instruction, so x86 can be anything from 1 to maybe 17 bytes or something crazy like this, which is of course horrendous and enormous. And the only benefit is that this compresses the program executable quite a lot. Although it's super complex, right? But the only benefit is memory and cache utilization. So on x86, you usually have much better cache utilization, and I think I remember some research papers that called out that on RISC you usually have like twice the cache and at least twice the cache for similar cache utilization than x86. And why this is, you see here already on this kind of compressed instructions. If you would not have this compressed instructions here, you would have, for example, here twice the size of executables and opcodes of memory used. And the same is, so PowerPC, as far as I remember, everything 32-bit uniform. If I say something wrong, just correct me. Also Spark here similar. You see here the Spark either instruction set architecture of Spark version 9. Exactly the same stuff here, call instruction, and then different formats here. This is of course instruction formats with the page intentionally left blank for whatever reason, and then different formats here, similar to what you've seen on RISC-V. You see, if you know one instruction set architecture, you can usually reuse your knowledge to all the other ones. They're usually not that different, except if you're implementing an assembler or compiler, but from the other concepts, it's all more or less the same. And again, here on Spark, everything uniformly 32-bit instruction and no kind of compression here inside. The only difference is ARM, what you find in all your smartphones and maybe some routers. On ARM, they eventually realized for exactly here to improve code density and density processor since the ARM 7 TDMI, which, do I have it? Yeah, I have it here. ARM 7 TDMI, exactly what we have here in this Xeon from back in the day, 720 7 TDMI. This, by the way, these letters here are similar to RISC-V. In the ARM world, these are extensions like T for thumb and whatever the rest was, and then you have J for Java or something, whatever. And yeah, this is what thumb is doing, but in my opinion, the RISC-V concept is much more elegant, because on, by the way, is this camera in focus? Anyway, it doesn't really matter so much. On ARM, you cannot use them freely, you can't mix them. So on ARM, actually I probably wanted to Google this. On ARM, you cannot on a, yes, Xeon Revo, you have seen this already on theoretically on other videos of mine. On ARM, you cannot mix them freely like on RISC-V. So what you need to do on ARM is you need to jump, you need to have a whole code segment of thumb. So you might have a function or your main program, doesn't matter. So you might have one section of executable that is entirely thumb, compressed ARM instruction set. And so you need a special jump instruction and set a special I jump to a thumb compressed executable code segment stuff, like what Christian just asked, jump and link, what is a RISC-V disassembly? Know that one from PowerPC. Yeah, so exactly this kind of jump and link and stuff. So if you jump meaning you jump or call to another function or subroutine. For those who are new to this matter, jump instruction being you have a function and you jump to this function. Usually you have different instructions like jump or call. The difference being that call instruction usually do additional stuff like storing the return address for a subroutine call and stuff like this, and returns and doing exactly the opposite, popping the return address from the stack. Probably many of these terms are a little bit in depth right now, probably stuff for a separate video to keep this here below 45 minutes. And so again, for sump on ARM on sump, you need to jump to a sump compressed code segment, and also for sum2 probably also have not really studied sum2 yet, but so sum2 is eventually ARM figured that they need something more advanced, and this is why on ARM you do not even have sum but sum2, and was introduced with ARM 1156 core and also 2003. Sump extends the limited 16-bit instruction set with additional 32-bit instruction, giving the instruction set more breadth, thus providing a variable length instruction set. Aims to achieve code density similar to thumb with performance similar to ARM instruction, because the thing is what this compression is doing is limiting it's limiting, as you have seen on the regular 32-bit instruction on the RISC-V or PowerPC Spark, and ARM on the regular 32-bit encoded fixed length instruction. You have all the instructions that are available, like all registers, all 32-bit general purpose registers and everything. And on the compressed instructions architecture, as you've seen here in the RISC-V document, to start with, so they write exactly this. Typically 50 to 60% of the RISC-V instructions in a program can be replaced with RISC-V compressed instructions, which is probably pretty impressive, as you see here. Just what you see here: compressed, compressed, not compressed, compressed, compressed. So really many instructions are compressed here, which is pretty amazing, resulting in 25 to 30% reduction, code size reduction, and I think like 20 to 25% cache utilization or something. Comments in the audience: what is the license for usage of RISC-V? Either, I think, as far as I know, it's completely open source. I think there are no royalties or something. But correct me if I'm wrong, you could probably research this, but as far as I understand, it's completely open source and free to use and so on. And so how does it compression work? Certainly this compression needs to have some drawbacks, right? And yeah, of course it has some drawbacks, yada yada yada, blah blah blah. So compressed instruction formats. And what this compression is doing is limiting, for example, limiting the use of registers. So as you have seen here, RISC-V has 32 general purpose registers, and in this compressed format you can't use all of them. You can only use, I think, 8 or something. Here shows the 8 compressed instruction. Oh no, this was unrelated. You see 8, mixing here 8, and this is 8, slipped here in the line. So are limited to just 8 of them, and lists those popular registers which correspond to registers 8 to 15. So with this compressed registers, you can't address all of those registers. So for example, you cannot, if you write assembly directly and you want to multiply a value or something, you cannot like multiply register 1 with 2. This would not be compressible, because you see you can only use register 8 to 15, and this is why the ABI, the application binary interface, is layouted in such a way to place the most commonly used registers in the register range 8 to 15, and making all of the other registers not as commonly used for better compression. If you would not do this, if you would not define the application binary interface, how programs, libraries and such call library functions, subroutines and such, and so on, and calling certainly the kernel for system calls. If the layout would not be placed so specifically, the compression would not be as high. Then you would not have this like 50% compression. If special care would be taken in this layout, then you would maybe only compress 25% of this instruction. So this is why the application binary interface was designed like this, to achieve the highest compression here in this setup. Comment in the audience, just wondering, could we have MIPS, RV, hyper-ISA CPU similar to MIPS, also free academia? Don't quite know what you mean by this. Do you mean by this that the MIPS ISA is completely free? Not really sure about this. Probably not. I think the MIPS implementer, something their imagination tech, or if it was sold in the meantime to someone else. Not. I guess previously they wanted licensing fees, or correct me if I'm wrong. And yes, so how does it look? It looks like this. What you have seen earlier in the beginning of my presentation here, that the regular instruction set formats here in RISC-V are all 32-bit, so these are only 16-bit, compressed, just what you have seen here in our compressed at whatever, at I, or what is I, is it, at immediate probably, to the stack pointer. So this is stack pointer minus 16, I guess, and that is compressed, this 16-bit. So these compressed instructions are half as wide, and here you see here's the opcode, and the rest of the opcode here is function 3 again. So this opcode only, this 2-bit opcode only signals I'm a compressed instruction, and the rest of the opcode, like add and so on. By the way, you see here the first 2 bits here always are I'm a compressed instruction, and the rest of the function I'm add, subtract, multiply, divide, call, and so on are here in the function 4 or 3 bits here on the top part. Then of course here the rest of the compressed jump target, offsets, immediate values, source and destination registers, and so on. And again, of course, the source and destination registers are much smaller here. Only 1, 2, 3, 4, 5 bits. For, is it 5? 1, 2, 3, 4, 5. It should be 2 to the power of 5. Is it 8? Here also immediate bits. For the 8, should it not be 4 bits? 2, anyway. And comments in the audience, RISC-V ISA is free and open to use by anyone for all types of information without restriction, seems to be CC. Yeah. So if we compare this to the regular instruction format here, that is of course reducing here the fields for the registers, source and destination registers, and that, to look this up again, is somewhere here it was. So yeah, you see here the fields for the destination and source registers. Destination register here, source 1 and 2 registers, so they are probably 7, 8, 9, 10, 11. So these are 5 bits. What did I say earlier? Some of this doesn't end up entirely. Anyway, you get the idea. And what is so interesting in this is that you can freely mix this. This is a huge difference to ARM. I'm not really sure if this has an advantage. Of course, in ARM, if you limit yourself to just the registers available in thumb code, then you can have a whole function in compressed thumb mode. But here you see that this compression happens completely intermixed with all the regular instructions, which is pretty interesting and a cool feature. And to show you further how this works in practice is, by the way, compressed. So how this works is, to take a look on the compression again, you see here we had 2, here's the compression extension. So you saw here from the opcode, the base opcode was 2 bits. And you would wonder, how does this compression setup work? And I think from what I've seen, the opcode for compression might always be, so this is slightly irritating here. Load install instructions, so this is compressed. I'm not really sure if this is 2, but we can maybe verify this in a second. 2 of course would mean that the first bit is 0. Anyway, this is slightly, but although I think that they mean here bits, so this is slightly misleading here in my opinion, could be slightly better formatted. So all this compressed instruction have a fixed value here on the first opcode. We see this adds up with the opcode listing. Let's shortly try to find the opcode listing here, because somewhere here is a list of all opcodes. And you will see that all the regular opcodes, if I ever find it here, here, I think so. You see all these regular opcodes are compressed. Okay, so you see all the compressed opcodes here have either zeros or 1 in the compressed. Oh no, they also have 2. Anyway, quadrant 2. Anyway, so because how does it work? Okay, so all the compressed opcodes here have 0, 1 or 2 apparently in the first bits here for the compressed. Let's better hope this adds up, because how does it work internally? Of course, when the processor fetches an instruction, it needs to decode this. So it needs to be, all the space of instructions needs to be used in such a way that certainly there are no duplicates. You can't have one instruction, the bits for the opcode here overlap. Certainly this wouldn't work if this would not be some identical mapping. This means all these bits here needs to be unused, not to be used in the same manner for non-compressed instructions. This is why I also said that these bits here, as you see, are all the same, and the function is defined here in the higher opcode in the 3 bits here. Just for example, here's a no operation. By the way, fun fact is mostly zeros, and the 1 is a NOP instruction. But then you see, because the compression indication here in the first 2 bits of the opcode is always the same, you see that the function is defined here in the higher bits. For example, sub, XOR, or and so on in those bits. And this better adds up when we compare this to the non-compressed instructions that also should be here somewhere. And they should all have these bits of the instruction not be set to either 1, 0, 1 or 2, wherever this here. And you see here what I just said a second ago, our compressed instructions. So these are the non-compressed instructions here, base instruction set are RISC-V 32i, integer, what this was. And you see here the opcodes are certainly larger here, the fields here for the opcode. As you've seen, the base opcode field was only 2 bits for the compressed instruction. And here you see all the first bits are all 1s, certainly marking, as far as I understood this here, marking all these instructions as not compressed. So all the non-compressed instructions start with the first 2 bits set, and then of course all the other here immediate values and so on. And also similar to the compressed instructions, what you see here, function 7 for example in the R type, because you cannot place all the instructions, all the available bit instructions, integer, multiply, divide, and logical instructions here in the lower fields here. This is why this R-type instructions here, for example, define, let's use a better example, or is this, yeah, this is maybe not too bad of an example. So you see here, they have here all the same bits set in the base opcode, but the difference is here in the function. So you see, for example, add is all bits 0 is add for the same base bits in the opcode here, and then for example XOR is still all the same bits set here, but XOR then is actually the difference is here in this field. I just realized they're all 0 there, but there you see even reduced instruction set, it's not so super easy. You see there are still multiple bit fields making up for this. Even I now looked in the wrong one. So there you see that shift right here is 101, XOR is 100, and subtract is 00 here, and there you see here add and subtract are here difference in this bit field. It's still 00 here, but then there you see even reduced instructions of architecture are not complex. They are also, well, due to the nature of all the complexity of computer science apparently still relatively complex, but you see all the low bits are set here to 1. And this probably is also one of the reasons why this is little endian, because with little endian you see these are the first bits here, and this probably is one of the reasons, I guess, not the inventor or implementer, I have not studied this here for a decade, only recently started to study this. But when you think about this, in your instruction, in your CPU, in your instruction decoder, you need to relatively early decide whether this is a compressed or non-compressed instruction. So if this would be big endian, then, and in general I'm quite in favor of big endian. Big endian means, probably could have Googled this for you, this means the order how this bytes of this 8-bit bytes of this 32-bit word are stored in memory. Endianness, Wikipedia. Although I don't like the Wikipedia entry here the most, because some of these diagrams are not the most amazing. Also some drop frames, damn it. As you can look up here on Wikipedia, and yeah, I don't like this diagram very much because this is slightly nah. But what this basically means is the order this is stored in memory. So we have here big endian, and big endian is stored in the same order that you would naturally write it down. So that order meaning you write this here down on paper like this, paper or digital PDF, and you would store it exactly in this order in memory. This also means if you look on a disassembly or on a hex dump, like you open your system memory in a hex editor, you would directly see the same order in a hex editor. That means big endian means here the highest value first. So if you have here coffee in hex written coffee, you would see coffee. And then if you have little endian being ARM usually, or x86 of course being little endian, is exactly the same, exactly the reverse order, meaning little endian starting with the little value, the first value here, the first value being this one, and storing this in memory first. This means, actually, in my opinion, this naturally is the reverse order, which is why I usually prefer big endian, because if you open your memory, or even a file, for example, you store your data in a file, like a bitmap or a WAV file, or just your instruction or a text editor with UTF-16 or UTF-32, and you open any of those stuff in a hex editor and take a look, then all those values are reversed. This is why I usually prefer big endian. Also, by the way, usually network order, when you send packets on the network, usually network byte order is big endian, meaning that on the wire the values are exactly transmitted how you see them here on this instruction set architecture PDF or paper, how you would naturally write down the whole number, which is, so network byte order is big endian. If you see this on an Ethernet cable or something, you see the values going through here in those readable order. However, for this compressed instruction set, the instruction is only 16-bit. And if the CPU would load 32-bit in big endian, it would have here this compressed instruction. Let's go back to the compressed instruction. For the regular instruction, it doesn't matter, they are all 32-bit. But if you load 16-bit, you have not the correct values, so to say, in, where is even ppack compressed? No, come on. You would not really have the same values naturally in your decoder, I think. It certainly is possible to make this to work, but I guess it is harder. Compressed instruction set formats, because as I've shown you, damn no, I pressed the wrong button. Can't make this up. Compressed here and then just a couple, and because as far as I see this here, let's go to some encoding table here. So you have 16-bit, and you don't know if you are the CPU or you implement the CPU and you start executing these instructions. Again, the first thing that you need to do is decode it, decode the instruction, because certainly to execute it you need to know, is it a jump, a move, an XOR, an AND, an OR, and subtract and such. So you need to decode the instruction, and when you start decoding you don't know if this is a compressed instruction or a non-compressed instruction. So you need to look on the first bits here in the opcode to decide, is it compressed or not, and if the CPU, probably a RISC-V CPU, I would guess probably always loads 32-bit, because half of the instructions can be 32-bit, so I guess it would make sense implementing this to always load 32-bit, and then decide, is it a regular instruction or is it a compressed instruction. And when you load 32-bit, then your low bits here from Big Endian are here, so you basically load more than your compressed instruction, and the first bit that differentiates this are then actually in the middle of the 32-bit value loaded. And this is probably, in my opinion, my guess here is, or my analysis is, that with Little Endian you start loading here this on the base address, so to say, on your current address, and this is when this is Little Endian, then your first bits are stored in this order. So basically here's from 0 to 7. So this is basically your first byte that you load, then your second byte, and then like some garbage or the next instruction. And this is probably why Little Endian actually makes, for this compressed case, a little bit more sense. Again, this is not a problem for PowerPC or Spark, because they don't have this kind of compressed instruction. They are all regular 32-bit long. But for this very clever integrated compression support here, it certainly makes sense to default or use Little Endian, because this makes the decoding, I guess, easier. And because again, if you try to visualize this again, if you load 32-bit, which goes over this 32-bit, then let's try to visualize this. Let's try to find this opcode map. I hope you maybe leave in the comments if you understood this already from my attempt to describe this here, because again, the 15 bits are here. So then, because if this is Big Endian and you load 16 bits, this are basically, so like from here, this would also, so the compression, the selection doesn't, apparently not, hello, can we select this? Using PDF in your browser, yeah, sort of. So if this is Big Endian, again, storing the big values, the most significant bits first, then our compressed 16-bit instruction would end up here in this higher 16 bits. And this certainly, as you can see, this would not be at the place where the decoder would start decoding this opcode. This is, if with Little Endian, it naturally ends up here in the lower bits. Although probably you could theoretically have designed this so that maybe it would also work if this opcode bits would be at the high address, maybe it would also work with Big Endians, because then naturally always if you load this, then you could probably have defined it the other way around. Anyway, I just wanted to point out this very special neat trick here. In my opinion, this is how I understand this here. Certainly very nice setup. Again, more elegant than ARM, because again ARM does not have this combined compression stuff, and again on ARM you need to jump a special, very special constructed jump to a thumb compressed stream. So this is a basic overview. Some stuff of this is not final. I guess this is already over my 45 mark here. Here again you see how this looks in practice with compressed and non-compressed instructions next to each other here. And some of the stuff is not final, so of course there is the first silicon, which I don't have because it is too expensive. Probably most likely we will do FPGA Pico RISC-V later this year on this channel if everything goes well, so you probably don't want you want to share, like, and subscribe, not to miss this FPGA fun with Pico RISC-V and stuff. Also some other notes. So by the way, time for comments in the audience. But I really try to keep this below 1 hour because otherwise nobody's watching this. Some additional notes. Right now in upstream glibc here on this T2 goodness here, upstream on Linux, there is upstream support in the Linux kernel, GCC and glibc and bin utils for RISC-V, but only for the 64-bit instruction set. So right now in T2, because of this, oops, that was wrong. Also, clean up, damn it. No. So right now T2 only supports upstream 64-bit RISC-V, which is slightly sad. There is on GitHub, in T2 by the way, there is a selection here. Also here, this is when you run here other cleanup stuff in parallel on Unix systems. So in T2 you can choose this here, but right now only 64 works because of the upstream limitation. If you configure here anything else, I think, yeah, I have already all options for future proving this, but right now it will not build. You could, if you really wanted to, you could import the upstream, not upstream, but GitHub on the RISC-V Foundation has on GitHub a special fork of GCC, glibc and the Linux kernel for 32-bit at least, maybe even 128-bit, not sure. Apparently the 32-bit application binary interface is not final. This is slightly sad because I would actually want it with Pico RISC-V on FPGA start with 32-bit, but that's not yet upstream. But 64-bit is, and the rest is certainly coming. But of course for the high-performance server and desktop on Linux, 64-bit makes the most sense. Just that you are aware, if you compile this open source today, you only get 64-bit upstream. Everything else is custom GitHub forks. Other shout-outs. I wanted to show you Intel 64 and 32-bit. Of course, this is, by the way, not Intel 64. This is, of course, AMD 64 because AMD invented this. Intel had Endianness, that was unsuccessful. And here you see how complex is x86. How many pages does it? Yeah, so 2000 pages, so much to complex instruction set architecture. And when you take a look on all the super complex instructions, of course, already the names PMUL something, this is an instruction probably not doing the right thing or something. This probably stands for, no, just a running gag, of course. And there you see already 30 years or something of Intel x86. This is how many instructions they produced. And again, I wanted to show you, if I find it here in this monster of a document, the variable instruction set encoding here. And somewhere here it should be visible, opcodes here. So primary opcodes can be 1, 2, 3 bytes in length. An additional 3-bit opcode field is sometimes encoded in the mod RM byte. Smaller fields can be defined within primary opcodes. Such fields define direction of operation, size of displacement, register encoding, conditional codes, sign extension, and coding fields used in opcodes vary depending on the class of an operation. So if you thought this RISC-V is irregular, yeah, then look on x86. This is super extremely irregular. 2-byte opcodes for general purpose and single instruction multiple data instruction consist of one of the following: an escape opcode byte, F hex as the primary opcode. And so there you see there are, even on top of this variable length, there are various escape opcodes for escaping here. Then there are mandatory prefixes like 66 that you have seen in my GCC DOS vintage stuff for overriding the operand and opcode sizes. So there is 66 and I think it was 67 for. Here's also F2 and F3 escape opcode sizes for the second. So there you see x86 is like compressed and variable lengths, but with all this like escape opcode, then you see usually like F and 66 and so on. And then you quickly get really like up to, I don't know, 15, 17, 19 byte long opcodes. And there you see, for example, PHA, so PH at V or something for XMM registers consists of the following sequences: 66OF3801. The first byte is the mandatory prefix. Valid opcodes are defined there. So there you see it is variable length and compressed, and then yeah, it is also 4 bytes. We could, by the way, for the fun, object dump here's some bin bash, and this, yeah. So here you see this here in real life. This is not the text section, so text hello. Maybe is this a start at base? Maybe. Anyway, and here you see, for example, as I said, some instructions on x86 are 1 byte, like pop. How is even drop frame something. So yeah, so FE is pop as an example of a 1 byte instruction. Also, no surprise there. Some push is also 1 byte, and there you see how this gets out of hand. Here, see move something is here with certainly some immediate, I guess, 4863D0, and here you see little endian. So here you see little endian at work, probably even the whole thing, because this is 00, 00 is probably here abbreviated, then 48, 48, 63, 63D0, D0, just here the reverse of natural writing order versus a little endian storage. And just as an example, so 1, 2, 3, so 7, I think here for move along something, and call quad here. So yeah, this is, and then by the way, good luck trying to write here an application specific implementation. Here some ASIC, some real x86 processor. Good luck implementing an instruction decoder for all this variable length fun. So certainly I would not want to implement x86 in logic gates. This is really totally not fun, as you can see here from the live example of the disassembly of our bash shell here. And as far as I remember, this can be much longer slightly. Wonder if we would have here some single instruction multiple data with AVX 512 or something. We certainly would have here some 11 byte long instructions or something. And yeah, this should be certainly be possible to find here in this instruction listing, somewhere in this 2000 page document. And if you want to have fun, you can go through this. If you want to have some good night read or holiday beach read or something. And yeah, you see this stuff here way more complex than RISC-V or Spark PowerPC and something. And if you implemented, in my opinion, if you implemented a processor with a complexity of x86, like a latest Core i9 or something, spending that many billion of logic gates on all the prefetch and branch prediction and caches and such with RISC-V, I would probably expect, but then again, actually the instruction set does not take so much of space here. The complexities, of course, that x86 processors of this day and age translate and decode the x86 instructions to internal RISC-like instructions anyway, to internal micro-ops. And then in the grand scheme of things, the instruction decoder for x86 actually makes up a surprisingly tiny amount, because of all the floating point is super huge to implement. And then on top of floating point, also floating point logic, all the single instruction multiple data. So you usually have, even not like in good old times where you had one floating point unit, nowadays you have multiple for all the single instruction multiple data, for example, to do like 4 floating point at a time in AVX 512 and things like this. And there you see, this is where the billions of logic gates are spent on all the single instruction multiple data for all the high performance multimedia stuff that you want for your MPEG decoder and 3D games and stuff. The last thing to point out is, speaking about single instruction multiple data, this is the only area where RISC-V is not yet fully defined. Here is an extension for, as you see, extensions RV32, so base integer as a guess there, and E for base, what E is probably embedded, I think, subset. And at least, why is it not written here? Base integer, what? Whatever. And here's already atomics and multiple and division, F for single precision floating point, D for double precision floating point, Q for quad precision floating point, L for logic decimal floating point, C for compressed instruction, and B for bit manipulation instruction, standard extension for dynamic translated languages. Oh, that looks interesting. J for probably maybe like Java, anyway. T for transactional memory. And then here packed single instruction multiplicator and vector instruction. You see this version 01 and 02. These instructions extensions here are not final. And it's also written here, discussed at the 5th RISC-V workshop, indicated a desire to drop the packed single instruction proposal for floating point registers in favor of standardization on the V extension for large floating point single instruction multiple data operations. However, there was interest in packed single instruction fixed point operations for use in integer register for small RISC-V implementations. So this is still research and development. And this also means here is V for vector operations, but even this is 0.2, so probably I would guess not written in stone yet. And this chapter presents a proposal for RISC-V vector instruction set extension. The vector extension supports a configurable vector unit to trade off the number of architecture vector registers and support for element width against variable maximum vector length. So yeah, not yet in the Core i9 performance department, but what I've seen here is pretty straightforward. How I would probably have done this if I would have done the research here for a decade or something. Sounds for the most thing looks quite logical. Although the different formats here, still a little bit many formats, but probably you can maybe not avoid this. What I've just shown you here is the different base instruction formats. Certainly here's this one, like this one. This is probably, on the first glance, it looks a little bit too complex for reduced instruction set, but certainly you can't avoid this with all the different kind of immediate values and all the different kind of bit field logic instructions and whatnot, and load store and this and that and so on. So most probably relatively sophisticated on at least what I've seen so far and used it for. And last but not least, and then we really end this video, here is of course the famous Agner's CPU block, and he has some criticism on RISC-V somewhere. He also writes about instruction set bloat, the new AV512 instruction set. This is, by the way, x86 Intel is at 300 new instructions. They use 300 new instructions just for AVX. Just if you wondered why your Intel CPU is not turbo boosting as much if it's running AVX code, you might probably know this, that the highest turbo boosts are probably only usually, as far as I've seen, reached with non-AVX 512. But yeah, not only super dense multiple packed floating or integer operations, so a lot more logic gates are in operation there, which is probably why it can't reach the same clock speed, I would assume. But additionally, this adds, as written here, 300 new instructions. So here 300 new instructions just for AVX 512. Amazing stuff, or maybe not. But he also criticizes here ARM and whatnot and CISC design and so on, blah, blah, blah. But he also had some, I think he had some criticism directly on RISC-V, maybe, although I don't see it right now. But anyway, Agner has here some forward comp for forward comp, what, not found? The document wasn't so much to what the heck. Anyway, he had some proposal for forward computational something, wherever that abbreviation was. So don't really think, forward compatible computer system, forward comp, and where he, as usual, says how to make everything even more amazing. Not really followed up on this. So here block, actually I think this link is just defect, as I just realized here. So damn it, hello. So this is just here some relative link instead of some absolute link. Come on. There, a little bit not snappy. It's the usual recurring theme here with So forward com, but I don't really see anyone using this in RISC-Silicon. But again, the more research and development, the better. Certainly more research always beats no research. The more we research, the more we learn. But of course, although maybe forward comp is more amazing, no idea, I've not studied this. What I've seen in RISC-V is pretty reasonable. The inline compression opcodes are pretty cool and usable. And yeah, leave me in the comments below what you think. Do you have already RISC-V silicon in your hands? The reason, the cheaper RISC-V is not supporting, I think, in memory management unit, so you can't probably not run Linux on this, I would guess. Of course, here still our usually reoccurring Linux stuff. On the FPGA, though, we will have Pico RISC-V of Clifford Wolf that also will not run Linux. So this is more of an embedded controller stuff for motor control and temperature control or whatever fun, like relay control and all the other fun control stuff you are doing. Also not Linux, certainly in just 512 bytes of memory or whatever you have on a very tiny FPGA. But nonetheless, I see my prediction for the future, and we will see in a decade how this is holding. I see MIPS and ARM disappearing. I see RISC-V taking over the world. But again, leave me in the comments what you think. What do you think about this, about the instruction set architecture compared to SPARC and MIPS and ARM and PowerPC and x86? Do you already have RISC-V? Where do you see the future, not only for RISC-V, but x86, ARM and MIPS? In the long term, I probably even see that x86 might even go finally away in maybe 5 decades, like 50 years or something, because this x86 is just too extremely super bloated, also with all the security vulnerabilities, Spectre, Meltdown, you name it. This stuff is so super complex, it's simply not secure anymore anyway, so maybe we should rather have a very high performance RISC-V stuff with really many threads, like thinking of a 64 thread or 128 thread. Maybe rather keep it stupid simple and massive parallelize it to have less security vulnerabilities and more streamlined implementation, and not this super complicated, not this huge monster cores that even Intel can't get right anymore, and maybe rather go massive ultra hyper parallel with a reduced instruction set architecture that people actually can get error free and vulnerability free. But again, that's it for today. Slightly longer than I anticipated. Dive here into RISC-V. As usual, when we start to discuss it, stuff gets longer and in-depth, and as usual. Thanks for watching. I hope you learned something. Comments in the audience, instruction set, hardware multiply. Yeah, so RV, iMac, probably this is the one without MMU, I guess. Now it has user and machine mode. Previously only machine mode. Ah, yeah, right. This sounds interesting. Again, for Linux, usually you want an MMU for a real MEMS operating system. Otherwise, it's more microcontroller stuff. Again, I hope you learned something and enjoyed this. Thanks for tuning in, and I hope to see you soon for all the next videos and live streams to come.